So our next presentation comes from Paolo Bianco from 4ITSolutions.
From Dell, actually.
/ Dell, yeah, okay.
Good morning, everyone. Before starting, let me thank again CSCS for hosting us today. It's such a beautiful place. It's really a pleasure to be here. Also, I want to thank 4ITSolutions, who is co-sponsoring with us our participation. And should you have any question that I will not be able to respond during the presentation, don't hesitate to come to the booth. We have also some nice gadgets to share. Okay? So, I am Paolo Bianco. I'm part of an EMEA team covering HPC and AI. The idea today is to give you, let's say, an overview of how the data center landscape is changing from a system manufacturer perspective. We are an end-to-end solution provider, and from a hardware perspective, a system manufacturer. Okay. If we open the door of a typical HPC data center, at today, that's probably what we will find inside. Big bunch of CPU nodes with an increasing fraction of GPU computing into the HPC space. FP64 oriented, not always, but it's very typical, this. Very power dense and very compute dense. Sorry. Power dense both in terms of computing power and electrical power. And adopting liquid cooling, in some cases, not always, mainly for density reasons. Now, question is this panorama going to remain the same in the future, in the near future? Well, probably not, because the effect of different forces acting, both from a technology perspective and from a workload perspective, will change the landscape. The first force acting is the increase in thermal design power of the chipset. I have reported in these slides the increase of the TDP of CPUs in the last 20 years. We have passed from 100 watts. The number is the top bin CPU in the family. And we expect to grow up to 600 watt per chip within a couple of years from now, which is a significant amount of heat and power consumption. Now, I understand that someone could say, but we are also increasing the efficiency, and lithography and other architectural challenges are doing something. Yes, we are increasing the efficiency. We have basically doubled the gigaflops per watt efficiency in 10 years. And we have increased or decreased more than halved the power consumption per core gigahertz. I have reported, oops, sorry. No, I was, there's no, I'm sorry, there was some laser somewhere, sorry. So I have reported these numbers in blue and in red are 4 examples of the top number of core on top bin CPU in that family, and I say the ratio between TDP and product of cores and gigahertz of the CPU. Now, I understand that we adopt several metrics into the HPC space, but the first metrics one usually adopt to understand how powerful is a compute system is how many core I have, how fast I run the core. So we are more than halved this number in 10 years, but that's not enough, because we have passed from 15 cores to 96 and even more cores. So the decrease is linear, but the increase of TDP is exponential. So basically, we are expecting to have an increase in power draw into the data center and some thermal load into the data center. If we give a look to the GPU landscape, we are observing the same trend. We are expecting GPU of 1.6 kilowatt to appear within 3 or 4 years, 1.6 kilowatt per chip. So if you have an 8-way machine, this will be 8 per 1.6 kilowatt, okay? Is the efficiency increasing? I have a reporting FP64. There's another slide about FP62. Yes, it is increasing because architecture are changing, and also chipset dimensions are changing, okay? If you have seen the latest NVIDIA presentation, Jensen compared the B200 with H100. This is twice the size, the chip, so it's twice the surface where we can spread the heat, basically. So again, the efficiency is increasing, but not keeping pace with the increase in power consumption. We are basically in what we call today the power war of the chipset manufacturer, where the focus for all the chipset manufacturer is to increase even and even more the computing power, adding cores both on CPUs and GPUs, regardless of power consumption. This means that we will be forced to adopt new architectures in the future, capable to cope with 8 or even 10 kilowatt per like unit of heat and absorbed power, and that's where the trend we observe in the near future, actually. So, first message, power will increase in the future, and there's no, no available technology capable to reduce this. This is not the focus of all the system and chipset manufacturer at the moment. But there is another force that is acting in order to change the landscape in the data center, and it is Gen AI. Now, what's the matter with Gen AI? With standard AI, with speculative AI, what we call as speculative AI, systems are aimed to take decisions and find relations between data and understand the context and take some decisions. Now, this requires a significant amount of computing power, significant amount of storage space and data, and so on. But if we move to generative AI, that means generate new contents starting from a big bunch of data, this requires order of magnitude higher computing power and processing. And given that the underlying technology is the same, this is changing a lot the landscape into the data center. I have reported here, I apologize, it's not too beautiful from a aesthetic perspective, this slide, but it's helpful. The power growth and the amount of power, the energy consumption for the single cleaning cycle for 5 different model size, okay? So, for example, for the training of 175 billion parameters, which is the size of GPT-3, I know it's old model, I will come later about this. In order to do a single training cycle in 7 days, we need 272 megawatts of power, a megawatt hour of power, and we need to have 1.5 megawatt of available power into the data center. Of course, if we have less available power and can use less nodes, we can still run the training, but it will take more time. To give you, let's say, a practical idea of what this means, I have reported the CO2 equivalent tons for a single training cycle, and the equivalent number of Jet A1, which is the fuel for flights, burned to produce this CO2. But I understood that saying you that a single training cycle takes 26 tons of fuel is not, maybe it's not easily comparable to something that we know. So I've asked to a friend who is a pilot, a flight pilot, to report this this fuel consumption to a typical flight, and the single training cycle of a GPT-3 model is more or less the same CO2 equivalent consumption of a B737 traveling from Fiumicino to San Francisco and back, with 300 people traveling, okay? So I understand that GPT-3 and these other models are quite old models, okay? We are now using GPT-4, and we expect GPT-5 or the equivalent Llama 2 or 3 models with probably 1 or 2 order of magnitude of billion parameters higher. But let me say that probably what we see as Dell, that the vast majority of customers will not end up doing training of very large language model. They will probably work into the fine-tuning space and inference space. And given that fine-tuning architecture is between 5% and 15% of the computing power of the first training architecture, this GPT-3 could well be, let's say, example could well be a fine-tuning system for the GPT-4 equivalent model. So that's something that we can have today. And if you want to have this today, let me emphasize that you still need 1.5 megawatt of available power. And by the way, a lot of money, because we are talking about 1,000 GPUs, which are not expensive, not at all, cheap. Now, okay, there's increasing computing power, but how far are we from an inflection point? I mean, can we expect the same ratio of growing power demand in the future, or will this stop at some time? The efficiency of the GPUs is still increasing. I've asked to Excel to report the best fit line, which seems to be kind of quadratic for NVIDIA and linear for AMD, but it is Excel. But on the other hand, okay, we have doubled or even more raised the efficiency, but we have grown several order of magnitudes the amount of computing power we need for doing artificial intelligence and large language models. So the answer is the inflection is nowhere near, at least at the moment. Unless you don't finish the money, so you cannot buy even more GPUs, the inflection is nowhere near. It is also interesting to see that the gray line on the bottom is the Moore's law, so there's probably some mismatch between needings and capabilities today that industry and NVIDIA first is trying to match in the future. So power density will increase, power draw will increase. We need several different architecture to cope with this demand. Okay, one could say, okay, power will increase, I will add more power, add more nodes, and let's continue as we did before. Unfortunately, there is another physical constraint coming out, which is the temperature package of the chipset will be forced to be lower, because there will be an increasing thermal production more or less on the same chipset side, the same, let's say, top of the chipset, and all the manufacturers are adopting staggered structure in the chipset. So in order to remove more heat from the same surface, I need to lower the temperature on top of the chip. So temperature of the chip will decrease, and this means that temperature of the data center needs to decrease, or on the other hand, it will be impossible to cool by air this new chipset. Because, well, from a physical perspective, it will still be possible, but it would require to have data center at 1 or 2 degrees Celsius or even less, which is, if you have a fridge, it works, but I mean, it's not what we want into the data center. The reality is that liquid cooling, which was a niche solution, mainly adopted for density reasons, is now becoming mainstream. There will be entire chipsets that will not be able to be cooled by air anymore, or if not sacrificing the density and the power consumption. Just to give you an idea, for an 8-way GPU machine that we have at our portfolio, but even competitors have, because the board is the same board of NVIDIA coming for everyone, the power draw taken by the fans into the system is around 2 kilowatt for over a 10 kilowatt power consumption. So it's 20% of the node power consumption, and will still need to grow at 6 or 7 rack units, so take a lot of space. For the current generation, the new generation will not be coolable anymore. So in order to be more efficient, we need to adopt liquid cooling as mainstream cooling method. Basically, because if we want to remove all the heat from the same surface, an increasing fraction of heat, we need to reduce the thermal resistance between the top of the chip and, I would say, on the chain, the outside air. I mean, heat is like the current, and temperature is like voltage. So if you want to increase the current, we need to reduce the resistance between two voltages. And that's the thermal resistance. We are now entering the region of liquid cooling thermal resistance with new chipset, and this will change the architectures in the future. What is interesting to see in this diagram, which I took from an Ashray white paper, I suggest you to give a look because it's interesting, is that if we depict this curve in the inverse of the thermal resistance in logarithmic scale, we can easily see three trends. So the first trend is the single core trend, where the degree of cooling difficulty has risen. Then up to 2017, it was more or less the same, and that's the reason why we have adopted air cooling everywhere, basically. And now we are starting to grow again within the power war trend. This is very clear from this diagram. Now, from a system manufacturer perspective, what are we doing at Dell in order to embrace these challenges? First, introduce liquid cooling in all our products, also the mainstream products. But before introducing liquid cooling, try to standardize the liquid cooling. The real problem today with liquid cooling is that there's no standard. If you buy a 19-inch system, whatever is Dell or HP or Lenovo or whatever other vendor here, you are sure that you can put the system in a rack because 19 inches is a standard wide, and each computing system has C13 or C19 plugs, which is, again, standard. Liquid cooling is not standard today. So each vendor is adopting different cooling media, different temperatures, different pressures, different connectors, different CDU, and so on, different methods. This doesn't permit to scale the economy and let's say, improve the innovation. Okay, so what we are trying to do at Dell, in order to enable interoperability, is to propose the standardization of liquid cooling with 15 standards within the OCP community. Only if we can have standard, we can make use of scale economy and enable interoperability. If we are able to standardize the liquid cooling, we could potentially have standard racks where you can put whatever liquid cooler machine from whatever vendor inside. That's a real problem today. That's the main reason why liquid cooling remains niche today, because there's no standard on top. We are working into the OCP community in order to let this standard to be approved. Now, what is our cooling strategy? Let's continue with air-cooled system, which will not be the top bin system. There will be some machines still air-cooled for, let's say, mid-performance chipset offering, and then some other machine liquid-cooled for top bin performance. Push on the standard and scale the supply chain once it's standard. If you think, well, it's the same that is happening into the x86 space. 20 years ago, when you wanted to implement a database, you call it DEC or HP or Sun Microsystem. By the way, I come from Sun Microsystem, so I know the story on the other hand. And Sun Microsystem or HP or other vendors bring to you the CPU, the operative system, the design machine, and maybe even the software running on top. So it was a closed stack. What was one of the main factors in order for the x86 model to succeed is that we standardize at the level. So there are companies focusing on integrating the system, doing let's say, system manufacturing and integration like Dell and others, companies doing CPUs, companies doing memory, and so on. This has reduced the cost and increased the innovation, and that's what we need into the liquid cooling space today. On the other hand, will we adopt 100% liquid cooling? The answer is no. We have never adopted 100% liquid cooling on our system. We will continue not to adopt 100% liquid cooling because we think that the return on investment is practically in the vast majority of cases, non-existent between a hybrid cooled system and 100% liquid cooled system. If we go further in time, the fraction of it not pertaining to CPUs and GPUs and vSwitch or other switches will be even and even less relevant. Today, from a GPU 8-way system, we are 90% of the heat or the power consumption is on the computing chips, and the remaining 10% is on the power supplies, memories, disks, and so on. We expect this to drop to 5% within a couple of years. And it doesn't work to engineer a complete liquid cooled system in order to remove the remaining 5% of it. This will require specific design, very expensive, with very high cost of engineering. So that's the reason why we will never adopt this approach. The approach is to adopt hybrid cooling and remove the remaining heat through closed loop system or cooled doors. Basically, that's on the bottom, it's what we do today. We have done today in the last 10 years, use 20 degrees water and remove the heat through liquid cooled doors. Or all the heat or the remaining heat not removed by direct liquid cooling. We have developed with some partners a solution capable to remove 100% of the heat, so to appear from outside like a 100% liquid cooled system. If I look at the system from outside, they are just pipes, water pipes and power and network entering. There's no communication between, there is no interaction between the data center space and the machines. And we are able to cool the system and to collect 100% of the heat through tempered water up to 32 degrees. By the way, 32 degrees is not a value dictated by physics or the heat exchanger into the system, but is what actually Ashray and Meta and other OCP community recommends as standard cooling temperature today. And they are also recommended to design the system in a way that the liquid temperature can be dropped to 27, which will be needed in 2 or 3 years from now. So if you are to design a cooling system, start from 32, but make sure that you can drop down to 27. That's basically how the heat collection with 32 degrees water works. Not rocket science, no rocket science, just an heat row system contained into a cage where we remove all the heat from CPUs and GPUs with direct liquid cooling, and the remaining heat to this purpose design heat exchanger, which is basically a radiator and some fans, capable to use water at 32 degrees and maintain the intake temperature of node at 35. All Dell products are certified to run at least at 35 degrees intake temperature. With at least, I mean that we have a configuration capable to run at 40, even 45. On standard system, I'm not talking about military system, that's another story, okay? So this is what we are adopting today in order to remove 100% liquid cooling. Thank you. And, but this is not enough. I have the last slide. This is not enough. In order to embrace this change and this power draw, increase in power draw, we need to change completely the architecture of the system. This is a design we are working on. There will be new machine based on this design philosophy using OpenRec version 3 standards. So machines will be, I've been blamed by colleagues because they say you don't have to mention blade. This is a multi-node system. But think as a blade system. So we have some blade within this rack. And all the power distribution and the liquid cooling distribution and the back planes will be on the back of the machine of the rack. And we can mix and match within this design power supplies, CPU nodes, GPU nodes, networking, and so on. This architecture is being designed for growing today at 300 kilowatt per rack. So you can have one rack drawing 300 kilowatt, which again says that the problem today is not to implement and computing power, but it's to power the system and cool the system. So, and in the future will be this process. So we are working on this design in order to release a completely new family of machines, and all the top bin, I would say the compute intense product families, both in terms of GPUs and CPUs, will be released under this form factor. That will be really, I would say, to match the needings for the next 10 years, more or less. We are in the OpenRec community, open compute community, because we leverage the standards and are part of the community. If you are interested, please come, we can have a discussion. I cannot show more because it's still under NDA, so basically. Okay, I think I can stop here. I just want to add one thing that I cannot put in a slide. We need to keep in mind that the vast majority of investments today, both from chipset technology manufacturer perspective and system manufacturer perspective, are on Gen AI, which has an enormous amount of money, orders of magnitude higher than other market verticals. So all the new architectures and products and technologies will come and will be aimed to Gen AI, or will be designed with Gen AI and artificial intelligence in mind. This means that it's the other compute that needs to adapt to this technology. We cannot expect to have technology for standard HPC happening anymore. It's the HPC to adapt to the AI architecture and technologies, because that's where the investment is, that's where the money is. But I didn't find a way to put on a slide this. But this is important to keep in mind, okay? You have to adapt to use something that is conceived for Gen AI and adapt for other things, because that's where the money are. So I think I can stop here. We'll be more or less in time. If you have questions.